So the topic today will be actually a comparing study of two different processes used in wire arc additive manufacturing. So the concept of in situ vibrations compared to the post-processing laser shock cleaning. So for starters, just to show what wire arc additive manufacturing is, it's actually one of the additive technologies that uses the direct energy deposition. Its main advantage is that it's based on the already exciting welding processes such as gas metal arc welding and gas tungsten arc welding. It has one of the highest deposition rates among all the additive technologies, somewhere from the 50 grams per minute to 130 grams per minute. Because it is based on the welding processes, a high selection of materials is possible. Let's say stainless steels, aluminum alloys, copper alloys, and so on. And we can also manufacture quite a lot of big scale products. So the equipment of WAM is shown here. So we have this existing welding process. So arc source equipped with fire feeder. In our case, the wire was aluminum magnesium 5. So aluminum alloy with 5% magnesium. We employ the shielding gas argon because it's inert gas, so to not contaminate the liquid melt pool. We had a 6-axis manipulator equipped with a gas metal arc welding torch to execute our trajectory of the welding. And the main process parameters that define our end functionality of the wire arc additive manufactured products are arc current, arc voltage, and speed of the torch, which also define our heat input. And the last, also very important parameters is the interface temperature, which is defined as the temperature at which the deposition of the next layer occurs. Because this method of using WAM is quite robust and has certain problems, because of the thermal cycling, high cooling rates, and unstable process parameters, a number of defects can happen. Among most important ones is the occurrence of gas porosity, especially in aluminum alloys due to hydrogen solubility. The other one is oxidation. This one is an example for the maraging steel. Residual stresses because of the thermal cycling and high cooling rates. Also microstructural inhomogeneities, such as the, let's say, microstructural anisotropy because of the directional heat transmission towards the substrate, and the waviness because it uses deposition layer by layer. So the conventional approach to mitigate these defects is through the different post-process methods, such as heat treatment, let's say solution annealing or homogenization, surface processing, milling to reduce the waviness, and isostatic pressing for reducing the porosity. But combining all of these methods can be quite time and energy consuming. So some efforts have been made in exploring alternative mid-process approaches, such as, let's say, interpass rolling, force cooling between the layers. And one amongst the most, let's say, promising is the usage of vibrations. Here we have our schematics, which is also our system employed in the laboratory. We have a frequency generator, which feeds into the vibration shaker. Through this rod, we transmit the vibration to our linear guideline. So the purpose of linear guideline is actually to prohibit the vibrations from occurring in different directions and only occurring through the linear guideline movement. We also have equipped accelerometer for the vibration monitoring to actually have the stable parameters. So the main process parameters are the frequency, vibrational acceleration, vibration direction, and the type of frequency signal. In our case that was sinus wave. And for our research and experimental purposes, we employ two different configurations, so the vibration assisted and as built as the reference model. And the other post-processing methods is the laser shock peening. So we won't go much into details here because I believe everything has been already described. So here we have our video taken from the LSP process. This is actually almond strip, which was equipped, but we had a little bit of problems with that because we didn't get any deflection point, but rather elongation occurred, probably because of the inadequate parameters. So we chose the two different configurations. So the overlapping rate was 1200 and 2400 for the second configuration, and the power density of 4 and 8. So we observed the modification of oxide film, so before applying LSP and after applying LSP. And the LSP was conducted on as-built one wall, so without any previous milling or other processes. So we measured the residual stresses on the surface for 4 of the different samples. So as-built the reference model, vibration-assisted LSP1 and LSP2. We did that with the X-ray diffraction method. We didn't detect any of the compressive residual stresses on the surface after applying LSP, but we did get, let's say, desired effects of relaxation of residual stresses. Because as we can see in the WAM and the vibration assisted, the average values of the residual stress measurement are quite inhomogeneous. So we have tensile residual stresses and compressive residual stresses in different directions of the measurements. We also quantified the porosity. So because of this vibration assisted process and due to the mixing, we promoted the gassing of the pool. And as we can see, we had quite positive results for the vibration assisted sample. We started welding at the cold substrate, and because of the fixed interpass cooling time, the interpass temperature increased, and we got the best result at the higher temperature, around 170 degrees. That's because of the larger window of the solidifications in which the vibrations can have more impact on the degassing. As far as the porosity goes for the LSP, we quantify the LSP affected depth for both of the set of the parameters, and we determined that the LSP with a higher overlapping rate and power density was 285 micrometers. We also took some optical microscopy pictures from the cross-section of our manufactured products. We see that in as-built sample, the average grain area was significantly higher than in the vibration-assisted sample. And also with the lowest interpass temperatures plus vibrations, we also managed to actually annihilate the whole microstructural isotropy. That is defined as the ratio of the average length grain area in the Z and Y direction. We also did some EDS analysis from this middle section of the walls for the as-built sample and vibration-assisted sample. And we also see that the intermetallic phases, which are enriched in the iron, are way more homogeneously distributed than in the as-built sample, which showcases that actually some homogenization took effect during to the influence of the vibrations and mixing the pool. We also did the optical microscopy on the LSP process, but it was a bit tricky because we can see that because we treated only one side with LSP and the other side is untreated, we see this localized refining effect on the both sides. But someone would say maybe this is due to LSP, but it's not, because in layer by layer deposition, we have this heat influence zone or pre-melted zone in which the crystallization rate is quite high and the temperature gradient is low. So this is why we get this characteristic finer grain area. So no obvious effect on microstructure after LSP was detected. So maybe a TEM analysis would be more in order to determine if there was indeed any effect. As far as the waviness goes, after the LSP, we did the analysis on LSP treated side and untreated side as the reference model. And we figured out that the LSP1 set of parameters significantly reduces the height of the sharpest peaks, and thus leading to the smoother surface with fewer extreme fluctuations. And as far as goes for the LSP2, it also modified the surface properties, but into more frequent and smaller peaks. So we can say that LSP1 set of parameters was actually more appropriate for, let's say, optimizing the surface set. We also analyzed the waviness in our vibration-assisted products and as-built. Here we can see that in as-built product, we have quite some amount of waviness as compared to the vibration-assisted. This is due to the partial collapse of the melt pool induced by vibrations, because we have vibrations perpendicular to the welding torch. And here we can see in as-built sample, the waviness of the deposited layer. So with this partial collapse of the melt pool, we actually hinder the transition between the layers, thus leading to the lesser waviness. We also plunge all of our data in the table for the better comparison, and we see that the vibration-assisted process was actually the most impactful on the improvement of the waviness, followed by LSP1 process and the LSP configuration. So the conclusions are as follows. So in vibration-assisted one, we successfully reduced the gas porosity, reduced the waviness, got some refining effect by lowering average grain area by 25%. And we also confirmed the homogenization effect induced by vibrations. As far as goes for the LSP, we got quite good results with the annihilation of gas porosity and LSP affected area, more for the LSP2 set of parameters. We also did reduce the waviness on the surface for both of the configurations. Relaxation of residual stresses was observed for both of the configurations, and the modification of passive film was observed, which will be a very important aspect in the future electrochemical corrosion testing. So this is our conclusion. Our goal for the future research is to combine these two processes and to study the highly promising potential of the synergic effect of both the LSP and the WAM on the waviness, electrochemical corrosion testing, and the properties and mechanical properties. Thank you.